The last and most important application of Lenz's law is, of course, generators. Now, just like with our previous demonstrations of Lenz's law, I just want to point out that this is not an explanation of why something is happening. Again, that comes down to Faraday's law, which ultimately says that, well, when we get a magnetic field, it's going to actually cause the charges, the positive and negative charges, to actually separate, which creates a potential difference. When we talk about generators, we call that an EMF. And ultimately, that potential energy that's created there causes the charges to flow. So that's sort of the why behind it. But we're going to talk about in this video is the description of how the current direction is determined, and ultimately that's going to come down to Lenz's law. So we can see that a generator has a very simple setup. It's got a wheel here so that you can actually turn the coil, and I've got two magnets here. And the blue, the significance of the blue is that, of course, this is going to be a south pole that faces the coil. This is going to be a north pole that faces the coil. And back here we've got our different commutators, because this can actually be an AC or a DC generator. Okay, so we can see that here we've got this is for DC, and ultimately this is going to be a split ring commutator. And I can see that this side here is for AC, and we've actually got slip rings there. And we'll talk about that a little bit later. Now, just to start off with, let's talk about the mechanism. What's actually going on here? Well, we've got a magnetic field. Well, it's going to go from the north pole towards the south pole. So we know that it always comes out of the north, goes towards the south. So my magnetic field is this way. Okay, using my fingers, it's going to go across that way. So from north towards south. Okay, and as I'm actually turning the coil inside that magnetic field, well, we're actually changing the flux with respect to time. Because remember that flux is going to be the number of field lines that actually pass through the coil. Okay? And we can see that well, let's look at it in the horizontal orientation. And I can see that I'm going to actually have maximum flux in this case, because we're going to get a maximum number of lines that are going to actually pass through the cross section of the coil. Okay, and actually one of the ways that flux is actually defined is it's actually defined as the perpendicular component of the field lines that ultimately pass through the cross-sectional area of the loop. It's a bit of a complicated definition, so I think an easier way to think about it is that, well, when we've got them perpendicular, so obviously the loop is oriented this way, we've got a maximum number of field lines that pass through it. We define that as the flux, and so we can see we've actually got a maximum flux when it's in the horizontal position. Now let's contrast that with what's going on in the vertical position. If I can get it to stay there, I might have to manually do this. Now it's in the vertical position, and I can see that this is the cross section of the coil here, and I can see that because the magnetic field lines go from north to south across like this, that I've actually got none of the lines actually pass through the cross section of the coil, and so we say the flux is actually zero. So we are going from maximum flux at the horizontal orientation, and as it rotates it's going to a zero flux at the vertical position. Okay, so we're actually getting a change in flux with respect to time. And as we learned from Lenz's law, when we get a change in flux, ultimately, just like with the magnet moving in and out of the solenoid, that's going to cause current to flow through this loop, and effectively we've actually generated electricity. So let's talk a bit about the current direction and how we can actually apply Lenz's law in this case. Okay, so I can see that as I mentioned earlier, so the flux is going to be to the right, right? It's going out of the north and into the south, and let's say it's rotating this way. So that means that we're going to have the fluxes to the right, and as we talked about, it's going to actually be decreasing, and will actually decrease to zero. Okay, so maximum to the right, and now it's decreasing and eventually becomes zero at the top. So now Lenz's law tells us that the induced flux in the coil will oppose this, right? So we've got our flux is to the right and decreasing. What's the opposite of to the right and decreasing? It's going to be to the right and increasing, isn't it? So my thumb then points to the right. My fingers are then going to trace the current direction, and I can see that it's a bit difficult to sort of get my hand in there, but I can see that the current's going to sort of flow around this way. Okay, so looking at my fingers, like so, the current is going to actually flow this way around the coil. So it's going to go here, down around the bottom, and then back around the top. Okay, and that's the current direction in the coil as it's rotating from the horizontal position up to the vertical position. Okay, now let's talk a bit about what's going on from the vertical position as it's going to be rotating back down towards the horizontal position. So from the vertical position, well, we've got a zero flux. Okay, now the flux is always going to be to the right in this situation because, well, it's determined by the polarity of the magnets. That does not change. It's always from the North Pole towards the South Pole. So the flux is always going to be towards the right, but now as it moves from the vertical position back down to the horizontal position, I can see that now the flux is going to be increasing, right? And we're going to get a maximum flux again when the coil is horizontal. So this means that the flux is changing. Well, how is the flux changing? Well, it's towards the right and increasing. The induced flux is going to oppose that, so it's going to be to the left and increasing, isn't it? So my thumb then points towards the left, and now my fingers indicate the current direction, and I can see it's actually going to flow the opposite direction. It's going to, if I follow my fingers, it's going to actually go from here around this side and then back around this way. So the current direction is actually changed. This is sort of an interesting situation we have here. So just remind you that when it was going from the horizontal to the top, it went one way around the coil. And when it went from the vertical position back down to the horizontal position, the current then flowed in the opposite direction. So effectively what we have is we've actually got alternating current. Okay? So alternating current is actually very easy to produce. All we need to do is just attach one side of the coil to one terminal, attach the other side of the coil to the other terminal, and the current direction is going to be constantly changing, which means that the polarity of these terminals is going to be constantly changing. So it might be positive, this one might be positive as it goes upward, and the current direction, remember, it always flows from positive to negative, and then as it then goes from the vertical position back down to the horizontal position, the current direction has actually changed, and so now the other terminal is going to be positive and this one is going to be negative. So we're going to get an oscillating current inside the coil, what we call alternating current. Okay? So this sort of gives us an idea of how an AC generator works. As long as one side of the coil is always attached to the same terminal, and both sides of the coil are always attached to the same side of the terminal, we're going to get an alternating current that is produced. So alternating current generators, also known as alternators, are actually quite easy to explain. What's a bit more difficult to explain is direct current generators. And in order to understand how a DC generator works, we're again going to have to, just like with motors, we're actually going to use a split ring commutator. And we're going to have a bit of a talk about how does the split ring commutator, we know what it does with the motor, and we know how it ensures that the forces acting on a motor always keep it rotating in the same direction, but clearly with a generator there's something different going on here, but we're still using the same device, the split ring commutator. So we'll have a bit of a discussion about how does that actually produce direct current. It's important for us to note that we're not going to actually get a constant direct current produced in this setup. It's actually going to be a varying direct current. Now it is always going to be in the same direction, but it's not always going to be the same value in terms of how many amps it is. It's not going to be the same. It's going to actually vary a little bit. And it's going to vary based on Faraday's law and obviously the voltage. And now again, when we talk about voltage with generators, we're talking about EMF is the word that we use, the electromotive force, the thing that actually makes the current actually flow around the loop, okay, in terms of this loop here. And ultimately that's going to cause, if I connect an external circuit, cause current to flow around the external circuit as well, okay. That's going to ultimately determine the current direction. Now, the way that it works is that we can see we have a maximum flux when the generator when the coil is in the horizontal orientation. We talked about that earlier. We have a maximum number of field lines that actually pass through the coil. And at the vertical position, we actually have a minimum number of lines that pass through the coil. So we've got a minimum flux. In fact, it's going to be a zero flux. Now, the relationship between EMF and flux is that when they're basically opposites of each other, one is actually going to be described by a sine graph, the other is going to be described by a cosine graph. And so what we know is that when sine is at a maximum, so let's say at 90 degrees, Well, that's when cosine is going to be 0 degrees. It's at a minimum. Okay, it's at 0. Now, you can sort of guess which one's going to be which. So when we've got at 0 degrees, we've got maximum flux. So it would seem that flux is going to be given by cosine. And at 90-degree rotation, we can see that the flux is going to be 0. So it makes sense that, well, the flux is going to be described by a cosine graph. And of course, it's all cyclical. The functions that we use, of course, have to describe the motion. It's going to be a repeating motion for the flux. Maximum to 0, to maximum in the opposite direction, back to 0, and then back to maximum in the positive direction, and we see this cycling of the flux. Now, what that means is that the EMF is going to actually be given by a sine graph. And in fact, it's going to be the derivative of the flux graph. Now we're getting a little bit mathematical here, so don't really worry too much about that. The key point I'm trying to get across here is that when the flux is at a maximum, that's when the EMF is at a minimum. So we've got maximum flux right now. That means that my EMF is going to be at 0. And that means that at the top, we're actually going to get a minimum flux, which means that we're going to have a maximum EMF. So we have a maximum voltage at this point, at the vertical orientation, and so that's when we're going to actually get our maximum current. Why? Because voltage is what causes the current to flow. So when the voltage or the EMF is at a maximum, the current is going to be at a maximum. When the EMF is at a minimum, it's at 0, the current is going to be at 0. So we can sort of see that the current is going to oscillate between a maximum value at the top here, at the vertical orientation, and then it's going to go down to 0, and then it's going to go back up to a maximum value, and it's going to go back down to 0, and on it goes. So we're not going to get a constant direct current. That's not what's going to happen. We're going to still get an oscillation that's going to occur, but we're just not going to get any current flowing in the opposite direction. It's going to go up to a maximum, back down to 0, then back up to a maximum, back down to 0. It never actually changes direction. Just the magnitude of the current changes over time.